everyone, welcome to InsightsByRish. In today's video, we will try to understand about self-attention mechanism in detail. Now, the self-attention mechanism is the core concept of transformers, and hence it's very important to know everything about the self-attention layer. After understanding about the self-attention layer, we will even see how the mathematical computation inside it happens. So coming back to the presentation, we will start with it. First, as you know, this is our transformer architecture. Now, this particular image is taken from the Attention is All You Need research paper. This is the entire transformer architecture from which we will be deep diving into the attention layer. So, in this transformer architecture, you have two significant portions, or you can say two significant blocks. The first one is encoder and the second one is decoder, as you can see. Now, this self-attention layer is present in both encoder as well as the decoder. There is just a very slight difference between the functioning of both, but we will try to focus on the attention layer of the encoder first. So if you take the look at the encoder portion, you can see that there are two significant sub-layers present in this encoder. The first one is the feed-forward neural network along with the normalization layer, while the second sub-layer is the attention layer along with the normalization layer. So we are going to focus on this particular sub-layer of the multi-head attention. Now, as you can see here, in this attention layer, first you pass the inputs, then you are getting the input embedding, then the positional encoding, and then we pass the output of that positional encoding to multi-head attention. We will try to cover all these things. We will try to see what's positional encoding, what is input embedding and all those stuff. But before understanding that, first we need to understand one significant thing, and that is that here they have mentioned multi-head attention. Now, this multi-head attention is a combination of many single-head attention layers. Now, to be more specific, you may ask that what is the number of single-head attention layers present in this multi-head attention. Now, that will purely depend upon the configuration and the use case with which you are trying to implement this particular concept. But if you take the look at Attention is All You Need research paper from which we have taken this image, and that research paper is the first proposed architecture of transformer. So they have mentioned that this multi-head attention layer consists of 8 individual single-head attention layers, as you can see here. One multi-head attention layer is a combination of 8 individual single-head attention layers, as you can see, head 1 up till head 8. Fine. So we will try to see what every individual single-head attention does, and the functionality of every single-head attention is similar to each other. So we will try to see what this individual single-head attention layer does. So if you take the look at definition of self-attention, you can see that self-attention is a mechanism within the transformer model that allows it to focus on different parts of an input sequence when constructing representations for each element of the sequence. Now, if I try to explain you this, what it basically means is whenever you are performing any kind of NLP task, whenever you are working with sequential data, not only NLP task, but whenever you have any kind of sequential data, in that case you want to construct some representations, you want to extract the context of the input. In that case, you want to analyze what each word in the sentence focuses on. Like in an input sequence, you need to understand that what's the relevance of each word with every other word present in the sentence. So for understanding this, we require the self-attention. The self-attention helps us to identify the relevance between two words in a sentence, what every word is focusing on, or which word has the highest correlation with which other word in the sentence. Let's take an example here. Let's say we have the sentence, the cat sat on a mat. Now this is the sentence, the cat sat on a mat, and we want to find the attention scores for this particular sentence. We will also see what these attention scores are. First, let's consider that this is a sentence, the cat sat on a mat. So it will construct a table for you, as you can see, and here you will have all the words from this sentence for which you want to find the focus. You want to find that this particular words are focusing on what. And as the headings also, you will have the same words that are present in your sentence. Now you will find the correlation between the words. Let's say the word the is focusing on itself with an attention score of 0.2. As you can see here, the word the is focusing on itself with an attention score of 0.2. Similarly, the word the is focusing on the word cat with an attention score of 0.1. So here you will try to build the focus of every word with every other word present in the sentence. So At the end, you will get this result. These are attention scores of all the words present in your input sequence. Now let's say you want to find the word sat focuses on which other words. Let's say that you have considered this word sat and you want to find, or you want to analyze that this particular word is focusing on what other words present in your sentence. So you will find the highest attention score for this particular sat word, and here you can see the highest values of attention score for this sat word is for the word cat and for the word mat. So the highest value of attention score for the word sat is for the word cat, followed by the word mat. Now when you take the look at single word sat, you won't understand anything from that single word. You won't understand any context basically. But the highest attention score for the word sat is for the word cat. That is, now you know that who is sitting. Basically, when you consider the sole word sat, you won't understand who is sitting, where he is sitting and all those stuff. But the highest attention score for the word sat is given to the word cat, that is of 0.3. So when you focus on that word cat, that is your word sat is focusing on the word cat. So from this you can easily gather the context that the cat is sitting. Fine. Followed by the word cat, next we have the word mat with an attention score of 0.2. Now here we know that the cat is sitting, but we also need to understand that where the cat is sitting to analyze the context. So here the second focus of the word sat is on the word mat, as you can see 0.2. So when you take these three words sat with a focus of 0.3 on the cat and with a focus of 0.2 on the mat, you combinedly get an context out of these words. You understand what the cat is doing, it is sitting, or basically who is sitting, that the cat is sitting, where is the cat sitting, on the mat. So from the three words itself, you are able to gather the context. And similarly, every word will have its own focus. So this is how the attention score helps us to find the focus of every word present in our sentence with every other word present in the sentence. Now, what are the important components of the self-attention layer? So if you take the look at the key components of self-attention layer, you can find that these three are the main components: input embeddings, queries, keys and values, and weight matrices. Let's deep dive into it individually. So first we will take the look at input embeddings, what that means. While working with the transformers or while working with NLP tasks, we pass the sequential data. And in this case, the sequence that we have is I love singing. Now, this is your input sequence, I love singing. Further, it gets tokenized. So in the tokenization process, we break that sentence, entire input sentence, into individual words called as tokens. So as you can see, the input sequence I love singing has been broken down into three individual words, I, love and singing. Further, then that words are represented with a numerical value. Here the value for I is 0.5, the value for love is 0.8 and the value for singing is 1.2. Now this is the input embedding of your input sequence. So instead of displaying I love singing, it will display the vectors 0.5, 0.8 and 1.2. As you know, the machines cannot work with the string data or with the character data. So here the input sequence is represented in a vector format. Now I have considered a single value for every word for the simplicity purpose. If you see in real, every word is displayed or every word is symbolized with the dimension of d. Let's say if the dimension is 3, then every word will be represented with a vector of dimension 3. As you can see, the word I is represented with a dimension 3, 0.5, 0.8, 1.2. This entire vector is representing a single word I. So similarly, every word in the input sequence might be represented with a vector of dimension d. Now the d can vary depending upon the use case, that will be your hyperparameter. But for simplicity purpose, here I have shown that every single word is represented with a single numeric value. Fine. So this was the input embeddings, and this input embeddings then will be processed with the positional encodings and will be further passed to the self mechanism layer. Now we will also try to understand what this positional encoding is in the later part of the video. Now first we will come to the second main key component, which is queries, keys and values. Now by just taking the look at definitions of this queries, keys and values displayed on the screen, you won't understand much, and hence I will try to demonstrate this query, key and value with the help of an example. Now if you say query, it represents the part of input sentence you are focusing on. Consider an example. Imagine you are working on a group project and you have different team members working on various parts of project. Now your ultimate goal of the project would be something like you would be having some use case, you would be having some aim of your project. So let's say that the aim of your project or the use case of your project is what are the latest market trends. This is what you are trying to analyze and visualize. So this would be an query. Now if you want to understand the word query in terms of this particular transformer, you can consider query like a question each word is asking about every other word from the input sentence. Fine. The second thing or the second word is key. Now key represents the information available in each part of the input sentence. Let's say again with an example, every member in your project will have their own expertise. Like every member will try to focus on different things. Considering this particular example where the use case is what are the latest market trends, let's say the member 1 will clean the data for you. He will perform all the processing and the cleaning of the data and will convert that raw data into an efficient one so that it will be easy for you to analyze and visualize. While the member 2 is having an expertise in visualizing the data with different charts. And the member 3 is having an expertise in analyzing the data, drawing the insights and conclusions from the visualizations prepared by the member 2. So here every member is having their own expertise. That is, every member is contributing something to the project. Similarly, the key is telling or the conveying you that what every word is contributing to the context. And the third part is value. Now value represents the actual information or the content from each part of the input sequence. That is, you will get the final output in this value part. Let's say member 1 cleans the data. Now this will be a process represented in the key. But when you will get the processed output data, that is the efficient data converted from the raw one, that will be your value for the first member. That is, in similar way you can say that the value will be the final output of all the pre-processed word embeddings. The member 2 will give you the final visualization charts as an output. The member 3 will give you the final data analysis report about the latest market trends. So this is a value that is representing the actual information or the content gathered from the input sequence. So this was the second key component of the self-attention layer. And the third key component here is the weight matrices. Now we have three distinct weight matrices. As we have three distinct features here, queries, keys and values. Similarly, we have three distinct weight matrices here. WQ, which is associated with query, WK, which is associated with key, and WV, which is associated with V. Now this weight matrices actually help us to find the query, key and value vectors. This weight matrices are initially they are randomly generated and then in the back propagation they will be updated. Fine. So when you want to find the query, what you do, you multiply or you take the dot product of your weight matrices for the query with the input embedding that you have achieved. As I have already told you about the input embeddings. So when you take the dot product of that input embedding with the weight matrices WQ, you will get the value for query. Similarly, if you take the dot product of your input embedding with the weight matrice associated with key, that is the WK, you will get the key. And when you take the dot product of input embedding with the weight matrices associated with value, that is WV, you will get the value. So this weight matrices basically helps us to find the values for queries, keys and value. Now, as I said previously, initially they are randomly generated, but later in the backpropagation process, they get updated according to the requirement. Fine. So this was the three key components of the self-attention layer. So this was all the theoretical part of the self-attention layer. But now let's try to see how actually mathematically this computation happens. Fine. So to understand the computation of the self-attention layer, we also need to understand some basic things before. Let me take these slides back to the attention layer architecture. So here you can see before passing the data to the attention layer, you have some processes done onto your input data. So when you take the input, it is converted into input embedding, then they are processed with the positional encodings and the output of that is further passed to the self-attention layer. Now let's try to see how this mathematical computation actually happens. So let me zoom in here. Now for the ease purpose here, to understand the example efficiently, I haven't considered the positional encodings here, but in the later part of the video, we will try to see how this positional encoding process actually happens. But here, to keep the example simple, I haven't considered the positional encoding. Fine. So we'll start with the example. Let's say your input sequence is hello world. So you will further tokenize their data. Let's say your first token W1 is hello and your second token W2 is world. Fine. After tokenizing this data, as I said previously, you convert that word into some vector format. Let's say the word hello is converted into x1 embedding, and the embedding for the word hello is 10. That is, the vector embedding for the word hello is 10, and the vector embedding for the word world is 01. So x1 represents the word embedding for the word hello, and x2 represents the word embedding for the word world. Fine. Now, as I said previously, I won't consider the positional encoding here because that will make the example more complex. So then, now we have to find the value of query. So as I said previously, this WQ is the weight matrix associated with the query, which will help us to find the value of query. So consider the value of this WQ as 11 and 01. Fine. Now to find the query, as I said previously, we have to take a dot product of this weight matrix associated with query, that is WQ, with the input embedding x1. Now the value of query, key and values will be different for every word. Fine. So if you want to find the query for the first word hello, you will take the dot product of WQ with the first word embedding x1. So as you can see here, your x1, which is 10, is multiplied with the weight matrix associated with q, that is 1101, and the q1 that you get here is 11. That is, the query for the word hello is 11. Similarly, for the second word, which is world, to find the query for the second word, what you will do, you will multiply or you will take the dot product of this WQ with the word embedding of the second word, that is the world, that is x2. So you will say x2 dot WQ, and you will take the dot product. So this x2 is 01 and this WQ is 1101. When you take the dot product of that, you will get q2, that is 01. Now this q2 is the query for the second word, which is world. Fine. So depending upon how many words you have in your input sentence, that many number of queries and that many number of keys and values will be generated. As we only had 2 words in this particular sentence, we just generated 2 queries here, q1 and q2. So this was the query generation process. We generated the queries q1 and q2 with the help of weight matrix WQ. Now, as I said previously, this weight matrices initially is randomly generated. Now we will take the look at the key generation process here. Now we have the weight matrix associated with the key here, that is WK, which is 1011. K1 is the key for first word, that is the word hello. So what you will do, you will take the dot product of this WK along with the word embedding for the word hello. So when you take the dot product, as you can see, your x1 is 10, that is your embedding, word embedding for the word hello is 10. So you will say 10 into WK, which is 1011, and when you take the dot product of this, you will get a K1, that is 10. Now this 10 is the key for the first word hello, and the same process you will also repeat for the K2. So K2 is the key for your second word, which is world. So what you will do, you will take the dot product of WK along with the word embedding x2. Now x2 is the word embedding for the word world, which is 01, and so you multiply this 01 with WK and you get K2. So this K2 is your second key for the word world. So now you got 2 keys for your 2 words that you have in your input sequence. So after this key generation and query generation, now we will focus on the values. These values will be our final outcome. For these values, we will have another weight matrix WV associated with the value. The same process we will again repeat. We will take the dot product of this WV along with the word embedding of the first word, which is hello. So you will say x1 into WV, and your x1, that is your word embedding for the first word hello, is 10, as you can see here. So you multiply this x1 along with this WV and you get the value as 01, which is referred to as V1. So V1 is your first value, that is V1 is the value for your first word hello. Similarly, you will generate V2, which is 10, and that will be the value for your second word, which is world. Fine. So now you have keys, queries and values generated for all the words that you have in your input sequence. Now you will calculate the attention scores. Now to calculate the attention score, let me tell you, if you have n number of words in your input sentence, then for every word n different attention scores will be generated. Let me take the example from this particular presentation. So as you can see here, we had 6 words in the input sentence. The cat sat on a mat. Here we had 6 words in our input data, and hence 6 different attention scores was generated for a single word. For the single word, the 6 different attention scores was generated. Similarly, for the word cat, 6 different attention scores was generated. And therefore, the number of attention scores generated for a single word will depend upon the number of words you have in your input statement. Fine. So here we had just 2 words in our input statement, which was hello world, and hence for every word 2 different attention scores will be generated. Now to find the attention score for the first word hello, the first word was hello, and we are going to find the attention score for that first word. So you will be using the query associated with the first word. Now for the first word hello, the query was Q1 and the key was K1. So what you will do, you will multiply your query of that particular word with the keys of all other words. So first you will say Q1 into K1. Now this Q1 is the query of the word hello, while the K1 is the key of the word hello. You will multiply that. Q1 is 1 1 and K1 is 1 0. When you multiply that, you will get the answer as 1. Then you will multiply your Q1, that is the query of your hello word, with the K2, that is the key of the word world. So K2, as you can see here, K2 is your second key. K2 is the key of the word world. And you will multiply that with the Q1, which is the query of word hello, to generate the second attention score for the first word hello, which is 2. So this 1 is the focus of the word hello on itself. If you take the look at this particular table, you can see this first word. If you try to represent this particular hello world in the terms of this table, you can see here you will, on the place of the, you will have hello, and on the place of cat you will have world. So 1 will be demonstrating the focus of hello on itself, which is 1, and 2 will be the focus of hello on the word world, which is 2. The same thing you will again do to generate the attention score for the second word, which is world. Now here, to generate the attention score for the second word, you will make use of the query 2, that is Q2, which is associated with the second word. Again, you will multiply, or you will take the dot product of your second query, that is Q2, with all other keys, with the keys of all other words. So you will say, you will take the dot product of Q2 with the key 1, that is the K1, which is associated with the word hello, and that will generate you an output of 0. Similarly, you will take a dot product of your query 2 with the K2, which is your key 2 associated with the second word, and you will take the dot product of that, and the answer is 1. Now this 0 is the focus of the word world on the word hello, which is 0, and this 1 is the focus of the word world on itself. Fine. So the score of your hello is 1, 2. As you can see, this 1 and 2 are the scores of your first word hello. So the score of hello is 1, 2, and the score of world is 0, 1. Fine. Now further you have to perform scaling. Now what is scaling? So now this hello has an attention score of 1, 2, and the world has the attention score of 0, 1. To perform scaling, what you do, you divide these values with dk. Now what is dk? Dk is the dimension of query. Let's see the query dimension here. If you see here, the dimension of our query is 2. That is, we have 2 values in our query. Q1 also we have 2 values, and in Q2 also we have 2 values, which means the dimension of our query vector is 2. So you take the root of that dimension. You take the root of 2. So as you can see here, your dk is the root of 2. And then you divide the values or the attention scores of these words with that root 2. So this is how you scale the values. You just take the root of your dimension of the query vector, and then you divide with that to their attention scores. So when you divide your first attention score of hello with the root 2, you get the answer as 0.71, and when you divide the second attention score of your hello with the value of root 2, you get the answer as 1.41. So your scaled attention scores are for the hello is 0.71 and 1.41, and the scaled attention score for the word world is 0.71. After scaling, you have to apply the softmax activation function onto that. So now you will be applying the softmax activation function on this scaled hello value. Fine. So after performing this, as you can see here, you will get the values as around 0.35 and 0.65. Then you will again apply the softmax activation function on the scaled attention score of the world, and then you will get the answer as 0.33 and 0.67. Fine. Now further what we will do, we will make use of the value in order to get the final output. Now V1 is the value associated with the first word hello, and the V2 is the value associated with the second word world. So what you will do, you will take the first value from the applied softmax function, which is 0.35. You will multiply it the value 1. Fine. So your value 1 is 0, 1. If you take the look here, your V1 is 0, 1. So you will multiply that 0, 1 with this first value of hello, which is 0.35, and when you multiply that, as you can see here, 0.35 into value 1, you will get this value 0, 0.35. Then you will take the second value from here, which is 0.65, and you will multiply it with value 2, V2. Now if you take the look at your V2, it is 1, 0. Fine. So you will say 0.65 into 1, 0, and you will get your answer as 0.65. Now when you take the sum of this, you will get the values as 0.65, 0.35 for the word hello. Same thing you will again repeat for the second word, which is world. So you will say 0.33, which is the first value here, and you will multiply it with value 1. Output of that will be 0, 0.33. Then you will take your second value, which is 0.67. You will multiply it with value 2, which is 1, 0, as you can see here. Fine. After doing that, you will get your final output as 0.67 and 0.33. Now we got the final output vectors for our hello and world. For hello it is 0.65, 0.35, and for world it is 0.67, 0.33. Now also keep this thing in mind that you just had two words in your input data, and hence just a vector of 2 dimension is generated as an output. Let's say if you would had 10 words in your input data, then in that case a vector of 10 dimension would have been generated for this word hello. Now what conclusion can we draw from this particular thing? So if you take the look at this hello, which has the value 0.65, 0.35, you can say that the word hello is paying more attention to the word world, about 65%, more than to itself, about 35%. Fine. That is, the hello is paying more attention on the word world with a percentage of 0.65 and just the attention of 35% on itself. Similarly, the word world is paying more attention on the word hello with a percentage of 0.67, that is 67%, while the attention just about 33% on itself. So this is the conclusion that you have drawn from this particular. As you can see, both these words are paying more attention on the other words than on it themselves. So this is how the mathematical computation happens. Now to make this computation easier, just let me minimize this. To make this computation easier, what I did, I considered very easy examples. I considered just two words, very simple values of vectors, again very simple values of the weight matrices, but in real they are very complex. This was all the stuff. But again, as I said previously, we skipped a very important step here, which is of positional encoding. Fine. Now what this positional encoding is, this positional encoding is actually a vector, and you process your input embedding x1 and x2 with that positional encoding vectors, and whatever the output is generated, that is passed instead of this x1 and x2. Here in this example, your x1 we directly pass the word embedding of x1, and on the place of x2 we directly pass the word embedding of x2. But instead what actually happens is, you actually process your x1 with the positional encoded vector and your x2 again with the positional encoded vector, and whatever output you get, that you pass on the place of this x1 and x2. Fine. So let's see how this positional encoding also happens. So this is the computation of positional encoding. Firstly, it's necessary to understand why this positional encoding is necessary. If you even take the look at this architecture here, just a minute, you can see here that you are processing your input embeddings with the positional encoding before passing it to multi-head attention. Now we also need to understand the significance of this positional encoding. Why is it required? Basically, in this transformer architecture, there is nowhere any kind of involvement of RNNs or LSTMs and GRUs. So LSTM and GRUs are basically recurrent neural networks. So in this entire transformer architecture, if you take the look at the entire transformer architecture here, you can see there is no involvement of any kind of recurrent neural networks in this. Now recurrent neural networks are not included here because recurrent neural networks, like when we work with recurrent neural networks, we can't process the task in parallel. There we have to perform serial processing. So in order to be able to process the data in parallel, that is to perform parallel processing, we eliminated the RNNs from these transformers. But again, that gave rise to a drawback. Now this RNN actually captures the sequence data of the input. Like when you pass the input, as you can see here, the cat sat on a mat. Here we cannot switch the words. Here we cannot say the mat sat on a cat, because if we switch the words, if we mess with the sequence of the words, then the entire context will be changed. So in order to understand, or in order to analyze the context, it's also necessary to analyze the sequence of the data, and that RNNs was able to capture the sequence of the data. But as in this transformer we eliminated the RNNs itself, we are not able to analyze the sequence of the data. We are not able to gather that sequence information to generate the context. Now we cannot include RNN here, because if we include that, we won't be able to process parallelly. But we also want to capture the sequential data. So what they did, they introduced a new term called as positional encoding, as you can see here. Now this positional encoding will be some random vectors generated, and that random vectors will be processed with your input embedding. So this positional encoding vectors actually helped us to capture the sequential data that we was not able to do because of elimination of RNN from transformers. Fine. So without the involvement of RNN in this transformer architecture, we were still able to capture the sequence data of the input with the help of this particular positional encoding vectors. So these are the formulas here for the positional encoding vector. Here we have two formulas of sine and cos, and they are used alternatively. For the first word, the sine formula might be used. For the second word, the cos formula might be used. And this is done to produce the randomness, to keep the randomness and to keep the alternativeness that they have in themselves. So here the POS, if you let me zoom in, this POS is the position in the sequence, the position of the word in the sequence. I is the dimension in total, and D of model is the dimensionality of the model. We will try to understand this with the help of an example. Considering the same example, hello and world. Now in the entire statement hello world, the position of the word hello is 1, followed by the word world. Actually here it should be world. Fine. So the position of the word world is 2, and the position of the word hello is 1. So the sine formula, so in place of POS, that is the position, position is 1. On the first place we have 1. Later then we have the dimension. We will keep it as 0, 1. So starting from 0, as you know, for the first word it will be 0, for the second word it will be 1, and for the third word it will be 2, and so on. Fine. So when you calculate these formulas, so you have 10,000 raised to 2i, so the dimension is 0 initially for the first word, and then the dimension of your model is 2, that is in your model you have 2 words. Fine. So the dimension of your model will be 2. So you will do 10,000 raised to 0 by 2, and the final answer that you are getting from the sine formula is 0.84, and from the cos formula it is 0.99. Fine. Similarly for the word world, if you take the look here, now the word world has a position 2 because it is present on the second position in your input data. So first you will have 2 in the positional encoding formula, and then again the dimension will 0, 1. For the first word it will be 0, for the second word it will be 1. Now when you process this in your sine and cos formula, the final output of the sine formula will be 0.9, and the final output of the cos formula will be 0.99. Fine. So now you have achieved the positional vectors, positional encoding vectors for your two input words. For your hello, your positional vector is 0.84 and 0.99, and for the word world, your positional encoding vectors are 0.9 and 0.99. As you can see here, for the word hello, first word the positional vector is this, and for the second word the positional vector is this. Now this is your initial input embedding. As you can see, initially you had this words hello and world, and then you performed word embedding on that, and the word embedding for the first word hello was 1, 0, and for the second word it was 0, 1. So this was your original word embeddings. So for the hello, the word embedding was 1, 0. What you do, you take a sum of this original word embedding 1, 0 along with the positional encoding vectors of the word hello. So when you take the sum of that, you get 1.84, 0.99. Now this is the value of your word embedding after performing the positional encoding. Similar goes for the second word. For the second word, the word embedding was 0, 1. Then you take the sum of that 0, 1 with the positional encoding vector of the second word, which is 0.9 and 0.99, and the final output is 0.9, 1.99. Fine. So this 0.9 comma 1.99, this 0.9 comma 1.99 are your word embedding for the second word after performing positional encoding, and this x1 dash and x2 dash, that is the results of your input word embeddings after performing the positional encodings, are then passed to this query formula. So here, instead of this x1 and x2, that x1 dash, this, as you can see, this x1 dash and x2 dash are passed, but here it would be very complex to perform all those stuff, and hence I skip this positional encoding stage here in this example. Fine. So just keep in mind, before passing to the query key and values into these formulas, the word embeddings are summed up with the positional encoding vectors, and the generated output is then passed to the query key and value formulas. Fine. So this was the mathematical computation that actually happens in the self mechanism layer. And as you can see, it was just the two input words, considering the very simple word embedding values and the weight matrices value. Initially, there are thousands of words in your input data, while the weight matrices values, the word embedding values are also complex. The entire this processing is very complex. Now this was for the self-attention mechanism for the encoder. Decoder, the self-attention mechanism in the decoder also remains same. The only difference would be that there it processes the numerical data to generate further the output. Fine. So this was the self-attention mechanism in the transformer with the mathematical computation that I already shown you, along with the positional encoding computation. Fine. So that's it for the video. Thanks for watching.